Alright. Okay. So chapter 2, yeah. Okay, high performance data processing, yeah. Alright. So outline of this chapter, we have some synopsis about the Flynn's taxonomy, some architecture, and some parallel networks, interconnection networks, especially on design of the topology. Okay, Flynn taxonomy, is a classification of computer system by number of instruction stream and data stream. Yeah. So we have single instruction stream or single data stream, single instruction stream and multiple data. Yeah. And then with multiple instruction and single data, and finally multiple instruction and multiple data streams. Okay. Okay, instruction stream. Yeah. We have a single data basically here with a single data and with a single instruction using traditional von Neumann single, CPU computer, and single data with multiple instruction like pipelining, and we have multiple data, multiple data. So using single instruction, So this one vector processes, fine-grained data using parallel computing, and also with multiple instruction and multiple data. We have a multi-computer and also multi-processor. All right. Okay. Single instruction first. Okay. Single instruction, if you can see here, with single instruction and single data, is a computer architecture in which a single unique core processor executes a single instruction stream to operate on data stored in a single memory. Okay, this is a concept or correspond to the von Neumann architecture. Yeah, we have control unit, processing unit, and also some memory. Multiple instruction, okay, and single data. Right. So it's a type of parallel computing architecture where many functional units perform different operations on the same data. Okay. So perform different operations. And pipeline architecture belong to this type. Okay, I believe some of you have learned this in OS class regarding pipeline, and also some, I think, in Netcom also there is pipelining. Yeah. So though a purist might say that the data is different after processing by each state in the pipeline, fault tolerance, executing the same instruction redundantly in order to detect and match errors, in a manner known as a task replication may be considered to belong to this type. Okay, this regarding multiple instruction and single data. And single instruction multiple data architecture. Computer with this architecture have a control unit in the CPU, that performs simultaneous operation on multiple processing element. Each processing element, or PE, has its own processing memory, and we can say that each unit will process a different data. Diagram to show single instruction multiple data architecture. Okay, so this is diagram to represent that. Okay, we have control unit, PE, processing element, and also memory. Where CU is a control unit, PE is a processing element, and M is a local memory to a processing unit. MIMD architecture. Computer design with this architecture have a set of processors that execute different operations simultaneously on different data set. There are two types of MIMD, okay, with share and also local memory. MIMD architecture diagram, you can see we have a shared memory and we have a single or local memory. Okay, these two things first they call shared memory and or this they call this term is local memory. Yeah. If shared memory processor and memory are the same computer. Processors share a single global memory. Processor communicate through a shared data value. Okay, we have processor, and then this is the infrastructure or interconnection network, and this is the memory. Okay, this is called shared memory multiprocessor. Okay, parallel architecture in multi-computer. A multi-computer is a multi-CPU computer without shared memory. Each processor only has direct access to its own local memory. The same address on different processor refers to different physical memory location. Since there is no shared memory, processors interact to each other by passing messages. Multi-computer. Multi-computer are connected through an interconnection network, okay, with infrastructure called some architecture topology. They are connected. Each computer consists of local CPU and memory unit. Okay, a processor only has a direct access to its own local memory. If a processor requires data from other computer, the processor communicate to each other using message passing mechanism. Okay, MP, message passing, MP, or MPI, message passing interface. A multi-computer is also known as a cluster computer. Distributed processor. Other names that refer to distributed multi-processor architecture, or non-uniform memory access. Component in the architecture and interconnection bus, more than one group connected to the bus. The group are CPU, cache, memory, and also I/O devices. Therefore, memory and I/O devices are distributed. Distributed collection of memory forms one logical address space. Okay. Distributed shared memory multiprocessor. Distributed shared memory multiprocessor. All CPU shared access to a virtual single memory. Virtual. This is referred to the local memory, virtual. Processor communicate through shared data value. Okay, this is scenario. Commercial vs commodity. Commercial means custom machine and switching network. Good balance between processor speed and communication network speed. Commodity constructed from mass-produced equipment like computers, switches, and etc. And also it's less expensive and also higher latency and lower communication bandwidth. Asymmetric multi-computers. A front-end computer interact with user and I/O devices. Back-end computers are exclusively for executing parallel program. Advantages: simple OS in back-end computers, easier to understand, model, and tune the performance of a parallel computing. Disadvantages: single point of failure. If a front-end computer is down, then the whole system is down. Scalability is limited by the performance capability of the front-end computer. Simple OS in back-end computer result debugging operation more difficult. Always need to use the front-end to display debugging report or messages. Require two distinct programs for every parallel application, such as front-end also back-end versions. Symmetric multi-computer. Every computer executes the same operating system and packages. Every computer has identical functionality. User may log in and develop program in any computer. Advantages: overcome disadvantage of asymmetric multi-computer that mentioned earlier. Disadvantages: difficult to maintain. The illusion of single multi-computer with user can log in into any machine. And also difficult to have consistent system performance due to workload of computer varying with time. Difficult to achieve high performance from parallel program because processors must compete with other processors for resources, especially CPU and also cache memory. Parallel architecture. Now regarding interconnection network or infrastructure. Multiprocessor computer use interconnection network to allow interaction between processors and also memory access by processors. Two main principles of interconnection network: shared medium and also switch medium. Shared medium will allow only one message at a time to be sent. Procedure of message transmission, listen and also send using broadcast method. If message collide or collision has occurred, wait randomly delay in time and resend. So issue performance degradation by message collision on heavily utilized shared medium. Switch medium support point-to-point message transmission among processors. Support concurrent transmission of multiple messages among different pairs of processors. Support scaling of the interconnection network to accommodate greater number of processors. Interconnection network, commonly remote data is required during the computation. Thus communication or connection is needed. Network connects between processor to processor. Using distributed memory architecture. Because of that, to provide physical path for messages sent from one processor or computer to another processor, in another computer, right? If there is an n nodes in the network, so n times n minus 1 divided by 2 of wired or links are required to ensure every node have a direct connection to each of other nodes. Interconnection network. If n is a high, direct connection between processors is not always the case in real practice. Instead, nodes are connected by indirect connection, which requires switch interconnection according to a network topology. Switch network topology. Categories of switch network topology. We have two: direct topology and also indirect topology. The ratio of switch network to a processor is 1. Number of switch equal number of processor. And the ratio of a switch nodes to processor node is greater than 1. Number of switch nodes bigger than number of processor. So there's some common topologies. we connect all these, yeah, all the devices or processor, either memory or computers. Okay, there are some, can see here some common network topologies. Yeah, we have star, 1D mesh, 1D one-dimensional torus. Yeah, two-dimensional mesh, two-dimensional torus, bus topology, star topology. Yeah, and butterfly we can see here, binary, 1 cube, 2 cube, 3 cube topology, 4 cube topology. Yeah. Interconnection network topology properties. Yeah. So diameter or D. Okay. We have some parameter. Just when we develop this kind of this infrastructure or interconnection or topologies here. Okay. Some parameter we need to recognize here, like diameter D, yeah, minimum number of links, shortest route between the farthest pair of nodes. This determines maximum distance or delay a message may travel and experience. Yeah, this also representing the performance lower bounds. And W means bisection width. Yeah, the minimum number of links that must be removed to split the network into two sub-networks of equal size. This determines ability to support simultaneous global communication. And bisection bandwidth, the maximum bit rate can be transmitted between two halves of the network, E or H, H for switch node, yeah, E capital, maximum number of edges or links, yeah, attached to any switch node. Okay, or vertex here they call. Ideally, E, capital E, is a constant independent of network size. Or L, capital L, stand for each length, yeah, maximum physical length of any wired link. Ideally, L is a constant independent of network size. Right. Switch network topologies. Okay, they will reflect to this, yeah. Okay, 2D mesh, yeah, network N equal D power of 2, where N is the of processor nodes in the networks. S equal N, where S the number of switch node in the network, or direct topology. Okay, for D, yeah, they're using 2 times square root, yeah, N minus 1. And for W, square root N. And for E, 4, and L equal, yes. Okay, this is some calculation, yeah, metrics for each of these topologies. Mesh network 2D or two-dimensional mesh network with equal 3, yeah. Switch network topology binary 3, yeah, N equal 2 power of D, S equal 2 times N minus 1, which is a direct topology. And to calculate D, so equal 2 log base 2 N, yeah, W equal 1, E equal 3, L equal no, yeah. So this will reflect to the parameter of each of these, yeah. So for 3, you can see processor 1, P1, P1, PO, P2, and P3, yeah. So switch network topology like a butterfly network, okay. Just give example just now. Can see N equal 2 power of D, S equal N log 2 N plus 1, yeah, in direct topology. And in order to calculate D, log 2 N equal 3, W equal N divided by 2, you will get 8, E equal 4, L equal no, yeah. So this one for butterfly topologies or network, yeah. Butterfly network with 8 processor nodes and 32 switch nodes, yeah. So processor, you can see and this is one rank 0, rank 1, rank 2, and rank 3. We have a processor PO1, PO0, PO2, PO3, PO4, 5, and PO6 and 7. Okay, how they connect using this butterfly network. And switch network topology, we have hypercube, also known as binary n cube. Yeah, so n capital equal to power of d, s equal n, which means direct topology. So d log 2 base 2n, w equal n minus divided by 2, e equal log 2n. Yeah, and L equal no. This one for hypercube network. So hypercube connected architecture, 0 dimension, first or 1 dimension, 2D dimension, 2 dimension, so the dimension, 3D dimension, yeah, and 4D dimension. Okay, interconnection network design issue. The design of interconnection network could influence the algorithm, implementation, and also performance of parallel program. For interconnection network design issue are bandwidth, number of bits that can be transmitted in unit, for example, bit per second. Second, cost of construction. And third is easy of construction. So this is issue in interconnection. And also we have a communication latency, yeah, capital T. So this is a formula, T equal Ts plus T base WL times L, yeah. TW is network latency, yeah, time required to send word of data, yeah. So T is the total time required to send data from source to destination. TS is a message latency. L is the length of data in words. So note TS must bigger or equal than TW for most of real parallel system. Example of parallel computers, we have here the Cosmic Cube, Touchstone Delta, and Intel Personal Supercomputer. And we have a project, Accelerated Strategy Computing Initiative Project, or ASCI. Okay, this is some example. The Cosmic, it was built in 1983, constructed out of 64 Intel 8086. Yeah, microprocessor, operating speed up to 5 to 10 mega flops. Yeah, so flops means floating point operation per seconds. This is the Cosmic Cube, you can see. And Touchstone Delta and Interpersonal Computer Supercomputer, HPPC. Touchstone Delta and Interpersonal Supercomputer, HPPC. Yeah. So further info you can get from this URL. All right. So Intel announced the IPSC, okay, /1 in version 1 in 1985 with 32 to 128 nodes connected with Ethernet into a hypercube topology. Okay, this IPSC. All right, and the Intel IPSC version 2 was 1987. The base setup being one cabinet with 16 Intel 8386 processor at 16 MHz, each with 4 MB of memory and 8386 co-processor on the same module. Okay, yeah, around 1987, correct. Instead of Ethernet, a custom direct connect module, yeah, was 8 channel of about 2.8 megabytes, yeah, per second data rate. Each was used for hypercube interconnection. Okay, this is the one, yeah. All right, Intel announced the IPS6/860 in 1990, yeah. The IPS6/860 consisted of up to 128 processing elements connected in a hypercube, each element consisting of Intel 860 and at 40 to 50 megahertz or Intel 8386 microprocessor. Okay, this is another IPS6/860. Okay. And Beehoove project, built in 1984 at NASA Goddard Space Flight Center, constructed from commodity computers and freely available softwares. Main issue, computing speed and communication speed are not balanced. Advantage, lower cost and rapidly improving performance. Okay, so if you can click here, the image of this Beehoove machine, yeah? All right. So this cluster, yeah, like a cluster computer, okay, you can see here. And this another example. Okay, Accelerated Strategy Computing Initiative project, yeah. So a project by US Department of Energy developed a series of 5 supercom. We have ACCI Red, ACCI Blue, and also we have Blue Mountain around 1999, yeah. And then we have SCCI White, yeah, on 2001, and also 2005, 2020, with 100, yeah, teraflops. Okay. So this, for this, you can see how this, yeah, they develop this supercom. In UTI, we've been used this long time ago. We have some Cray machine, yeah, parallel machine we keep using, but since we have a cluster, we're not using anymore. Yeah, all right. Okay, currently we have many projects like Google, Amazon. Okay, they provide this called cluster and free for you to access. I told you before. Okay, instead of Google, we have another company like Amazon. Okay, to provide this facility. Okay, what is the fastest supercom nowadays? So now you can check here. Okay, see the numbers of supercomputer. This is some reference. Okay, try whether we can see that. Okay, around 2022, yeah. All right, so you can check that link. Okay, so this is end of chapter 2. Okay, we stop for a while.